Tonight, we're going to explore something that sounds like it belongs in a philosophy class. Not a physics lab, but it's real, it's been tested, and it might be one of the strangest results in the history of science. Somewhere on Earth right now, in a laboratory basement, or aboard a satellite passing silently overhead, a pair of particles is behaving in a way that no signal, no matter how fast, could explain. Not a rumor, not a theory waiting for confirmation. A measured, repeated, Nobel Prize-winning fact about the universe you happen to be living in. In 2015, 3 separate research teams, working independently in the Netherlands, the United States, and Austria, ran an experiment that had been theoretically possible for decades, but practically impossible to close every loophole on. They took pairs of particles, separated them by more than a kilometer in some cases, and measured them in a way designed to rule out every conventional explanation for what quantum mechanics predicted would happen. What they found confirmed something Albert Einstein spent the last 30 years of his life trying to disprove. 2 particles, separated by real physical distance, behave as a single connected system, instantly, with no signal passing between them that any known form of physics can detect. 7 major discoveries, spanning 90 years of physics, from a 1935 thought experiment to a quantum computer running in 2022, all point toward the same unsettling, exhilarating possibility: that the distance between things in the universe might not be as fundamental as it feels. By the end of tonight, you're going to understand why some of the most respected physicists working today believe that space itself might be built out of connection, not separation. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. In 1935, Albert Einstein sat down with 2 younger physicists, Boris Podolsky and Nathan Rosen, and wrote a paper that was meant to end a debate. Quantum mechanics, the strange new theory describing the behavior of particles at the smallest scales, had been making predictions that Einstein found deeply uncomfortable. The theory suggested that 2 particles could become linked in such a way that measuring one would instantly determine the properties of the other, no matter how far apart they were. Not nearby, not across a room, across any distance at all, across a galaxy if you wanted to imagine it that way. It's worth noting that Einstein wasn't the first great physicist to feel uneasy about the idea of instant influence across distance. Isaac Newton, more than 200 years earlier, had wrestled with almost the identical discomfort about his own theory of gravity. Newton's equations described the gravitational pull between the Sun and the Earth as acting instantly, across 93 million miles of empty space, with no mechanism, no medium, no explanation for how that influence crossed the gap. In a 1693 letter to the theologian Richard Bentley, Newton reportedly confessed that the idea of one body acting on another across empty space, without anything passing between them, was, in his words, so great an absurdity that he believed no one with a competent understanding of philosophical matters could ever accept it. He offered his equations as a working description of gravity's effects, while openly admitting he had no explanation for gravity's underlying cause. It would take until 1915, and Einstein's own general theory of relativity, to finally resolve Newton's discomfort, revealing that gravity isn't really a force reaching instantly across space at all, but the curvature of spacetime itself, a distortion that ripples outward at, and never faster than, the speed of light. Here's the thing worth sitting with. The very physicist who solved Newton's 200-year-old discomfort about instant influence across distance would spend the final decades of his own career convinced that a new theory, quantum mechanics, had reintroduced the exact same kind of absurdity he and Newton had both found intolerable, only this time hiding inside the mathematics of particles instead of planets. Here's the thing. Einstein had spent his entire career building an understanding of the universe where nothing travels faster than light. It's baked into the structure of relativity, the theory he built brick by brick between 1905 and 1915. Cause has to precede effect. Information has to travel through space, taking time to do so. Nothing gets a free pass around that rule. So what's happening when quantum mechanics predicts instant correlations across any distance? Einstein believed there had to be a simpler explanation. He proposed that the particles must carry some kind of hidden instructions, baked in from the moment they were created, like two sealed envelopes containing matching numbers. Open one envelope in New York, and you instantly know what's inside the other envelope in Tokyo, not because anything traveled between them, but because the answer was decided in advance. He called quantum mechanics incomplete. He believed a deeper theory, one with these hidden variables, would eventually replace it and restore a universe that behaved the way common sense demanded. Physicists eventually gave this entire package of assumptions a name: local realism. Local, meaning no influence can travel faster than light, ruling out any kind of instant action across distance. Realism, meaning particles possess definite properties at all times, whether or not anyone is looking. The way a rock sitting in a field has a definite shape and location, whether or not a hiker happens to walk by and notice it. Together, local realism describes almost exactly how we intuitively expect the entire physical world to behave. And it's worth naming clearly, because everything that follows in this video is really the story of local realism's slow, rigorous, thoroughly tested collapse. Wait, it helps to slow down here, because this is the exact fork in the road where the entire rest of this video splits off from ordinary intuition. Let's put this in context. Imagine you have a pair of gloves, a left one and a right one, and you put each glove in its own box without looking. You mail one box to a friend on the other side of the world and keep the other yourself. The moment you open your box and see the left glove, you instantly know your friend has the right glove, even though nothing traveled between you at that instant. It's like knowing the answer to a question the second you learn half of it, because the answer was decided before you ever separated the two halves. That's the picture Einstein wanted to be true, predetermined, local, sensible. Quantum mechanics, on the other hand, made a much stranger claim. It said that the particles don't actually have definite properties until they're measured. Before measurement, a particle exists in something closer to a haze of possibilities, what physicists call a superposition. Only when you observe it does that haze collapse into one definite outcome. And here's the part that troubled Einstein most. If you take two entangled particles and separate them by any distance, measuring one doesn't just reveal a pre-existing answer, it appears to instantaneously determine the state of the other. Not send information about it, determine it, in the same instant. Einstein, Podolsky, and Rosen argued this was absurd. It would require what Einstein famously described in letters to colleagues as spooky action at a distance, a phrase that's echoed through physics ever since. He reportedly believed that no serious theory could tolerate influences that outrun light itself, and he was confident that once physicists dug deeper, they would find the hidden variables, the sealed envelopes that made everything sensible again. The paper was published. It became one of the most cited papers in the history of physics, and for nearly 30 years it sat there as a philosophical objection, impossible to test, impossible to settle. Both interpretations, hidden variables and true quantum weirdness, predicted the same statistical outcomes in every experiment physicists could run at the time. It was a stalemate. Not a permanent one, but it certainly looked that way to most working physicists at the time. Niels Bohr, Einstein's chief intellectual opponent throughout this entire debate, published his own response to the 1935 paper within the same year, arguing that Einstein, Podolsky, and Rosen had smuggled in a classical assumption about what reality has to mean before measurement even occurs, an assumption Bohr considered unjustified given everything quantum mechanics had already demonstrated about the behavior of light and matter at small scales. Most of the physics community, by the late 1930s, had sided with Bohr, not because anyone had definitively settled the question, but because quantum mechanics kept succeeding, again and again, at predicting the outcomes of new experiments with extraordinary precision, while offering no practical alternative that worked as well. Einstein remained unconvinced regardless, a minority position he held by his own account until his death in 1955. To understand why this argument had such staying power, you have to understand what quantum superposition actually looks like in a laboratory, not just in a thought experiment. Consider the most famous demonstration in all of quantum physics, the double-slit experiment. Fire individual electrons, one at a time, through a barrier with two narrow slits cut into it, toward a screen behind. Common sense says each electron should pass through one slit or the other, landing behind whichever slit it went through, building up two simple bands on the screen over time. That is not what happens. Instead, the electrons build up an interference pattern, alternating bands of high and low probability, the exact pattern you'd expect if each electron were somehow passing through both slits at once, interfering with itself. Physicists have run this experiment with electrons, with photons, with entire atoms, and even in a series of experiments through the early 2000s, with large carbon-60 molecules, sometimes called buckyballs, complex cage-like structures containing 60 carbon atoms each. The interference pattern still shows up. Even with something that large, something you could, in principle, see the shadow of under an electron microscope. Let me put that in context. It's like rolling a bowling ball down two separate lanes at once and having it interfere with itself in a way that changes where it lands, purely because both lanes were open. No bowling ball does that. No baseball, no thrown rock, nothing at the scale of everyday human experience behaves that way. And yet at the quantum scale, this is not a rare exception. It is the default behavior of matter and energy, confirmed in laboratories for nearly a century. Counterintuitive, almost offensively so if you're used to thinking in terms of billiard balls and solid objects. This is the strange backdrop against which entanglement operates. If a single particle can behave as though it's smeared across two possible paths at once, existing in superposition until measured, then a pair of particles can be entangled in a related but even stranger way. Their properties become correlated, not because each one secretly carries a fixed answer from the start, the way Einstein hoped, but because the pair, as a whole, exists in a joint quantum state that hasn't resolved into definite individual properties yet. Measuring one particle appears to instantly resolve the state of both. Between 1927 and the early 1930s, this argument played out publicly, most famously in a series of debates between Einstein and the Danish physicist Niels Bohr at the Solvay conferences in Brussels, a gathering of the era's leading physicists held roughly every 3 years. Einstein reportedly kept proposing increasingly elaborate thought experiments designed to show that quantum mechanics violated some basic principle of physical reality, and Bohr, again and again, found a way to show that the thought experiment was consistent with quantum theory after all. Neither man ever fully persuaded the other. Einstein never stopped believing quantum mechanics was incomplete. He wrote as much in letters until near the end of his life in 1955. So what's happening here that makes this matter almost a century later? It's simple. This wasn't a settled argument that faded into history. It was a live question, sitting quietly at the foundation of physics, waiting for someone to figure out how to ask the universe directly which version was true. And when someone finally did, the answer wasn't the one Einstein was hoping for. Wait, not quite a stalemate forever. Because in 1964, a physicist working at CERN named John Stuart Bell found a mathematical crack in the problem, a way to actually test which version of reality was correct. So what's happening here that makes this matter almost a century later? It's simple. This wasn't a settled argument that faded into history. It was a live question, sitting quietly at the foundation of physics, waiting for someone to figure out how to ask the universe directly which version was true. And when someone finally did, the answer wasn't the one Einstein was hoping for. But it gets worse for Einstein's version of reality, because Bell's insight didn't just reopen the debate. It gave experimentalists an actual number to chase, a threshold that hidden variables could never cross, no matter how cleverly designed. And once that threshold existed, physicists spent the next 60 years building increasingly precise experiments to test it. Let's talk about what Bell actually discovered, because it's one of the most elegant pieces of reasoning in 20th century physics. Bell realized that if Einstein was right, if particles carried hidden, predetermined instructions decided at the moment of creation, then there was a mathematical limit to how correlated the results of certain measurements could be. He derived an inequality, a simple mathematical statement, that any theory based on local hidden variables had to obey. Local meaning no faster-than-light influence. Hidden meaning the properties exist before measurement, whether or not we can see them. Here's what made this so powerful. Quantum mechanics predicted that under specific experimental conditions, entangled particles would violate that inequality, not by a small amount, by a specific, calculable margin. This meant the question was no longer philosophical. It was measurable. You could build an experiment, run it thousands of times, gather statistics, and simply check which side of the inequality nature fell on. If the results stayed within Bell's limit, hidden variables and local realism would be vindicated, and Einstein would be right after all. If the results broke that limit, quantum mechanics would be vindicated, and the universe would have to accept a kind of connection that has no analogy in classical experience. The first serious experimental tests came in the 1970s, and then, more famously, in 1982, when the French physicist Alain Aspect and his team ran a series of experiments using pairs of entangled photons, particles of light, generated by exciting calcium atoms. They measured the polarization of these photons at two separated detectors, switching the measurement settings rapidly enough that, in theory, no signal traveling at the speed of light could coordinate the results between the two sides. The outcome violated Bell's inequality, clearly and repeatedly. It looked like a decisive win for quantum mechanics. Aspect's setup, built at the University of Paris South, generated entangled photon pairs by exciting calcium atoms with lasers, causing each atom to emit two photons in rapid succession as it settled back down to a lower energy state. The two photons flew off in opposite directions, toward two separate detectors stationed several meters apart, close by cosmic standards, but far more than enough distance for the switching mechanism to matter at the timescales involved. The team used acousto-optic switches capable of redirecting each photon's path roughly every 10 nanoseconds. Faster than light itself could cross the gap between the two detectors, specifically to prevent any conventional signal from coordinating the results between the two sides during a single run of the experiment. Let's put the scale of that violation in context. The experiments didn't just barely cross Bell's threshold. The statistical correlation between the distant particles was strong enough that the odds of it happening by chance, if local hidden variables were true, were vanishingly small. The kind of odds you'd associate with flipping a coin and getting heads 40 times in a row. It's like calling a distant friend, asking them to think of any number between 1 and 1,000,000, and having them say the exact number you were thinking of every single time for 40 consecutive calls. That's not a coincidence you accept. That's a sign something deeper is connecting the two of you. But there was a problem, and physicists knew it at the time. Loopholes. Not scientific hand-waving, but genuine, technical gaps in the experimental design that a sufficiently determined skeptic could exploit to preserve a classical explanation. The detection loophole was one. In the 1980s, detectors were inefficient. They only caught a fraction of the photons produced. What if the photons that were detected happened to be a biased, non-representative sample, one that just happened to mimic quantum predictions while the full population of undetected photons actually obeyed Bell's inequality? It sounds like a stretch, but in physics, you don't get to dismiss a loophole because it sounds unlikely. You have to close it. The locality loophole was the second problem. Aspect's team switched the measurement settings quickly, but not quite fast enough, and not quite randomly enough, to completely rule out the possibility that some subtle signal, traveling at or below the speed of light, could have passed between the two measurement stations during the experiment and influenced the outcome. It's a narrow window, but in physics, narrow windows are exactly where hidden explanations like to hide. Let's dig into the actual mathematics for a moment, because it's simpler than it sounds. Bell's original inequality has a well-known variant called the CHSH inequality, named after the physicists Closser, Horn, Shimony, and Holt, who refined it into a form suitable for real experiments in 1969. The CHSH inequality states that a specific combination of correlation measurements, taken across 4 different measurement settings, cannot exceed the value 2 if local hidden variables are true. Quantum mechanics predicts that entangled particles can push that value as high as approximately 2.83, a number physicists refer to as Tsirelson's bound, after the mathematician Boris Tsirelson, who proved in 1980 that this is the absolute maximum quantum mechanics itself allows, even though it exceeds the classical limit. Here's what that means in context. It's like being told a fair coin, flipped honestly, can only match a distant partner's flip somewhere between 50% and 75% of the time under a specific betting scheme, no matter how cleverly the two of you plan your strategy in advance. And then discovering that when you use entangled coins instead, the match rate climbs to something like 85%, consistently, every single time you run the test, in every laboratory that's ever tried. That extra correlation, above and beyond anything classical planning could produce, is the signature Bell went looking for. Aspect's 1982 experiments measured values solidly above the classical limit of 2, approaching but not quite reaching the full quantum maximum, due to the imperfect efficiency of 1980s era detectors and photon sources. Still enough to violate Bell's inequality by many standard deviations, a statistical measure of how unlikely a result would be if it were pure chance. Many standard deviations in physics is not a marginal result. It's the kind of confidence level physicists use to announce the discovery of a new particle. Let's put standard deviations, or what physicists often call sigma, in context, because the term gets thrown around without explanation more often than it should. A result at 3 sigma corresponds roughly to a 1 in a few hundred chance of being a statistical fluke, respectable, but not yet the gold standard. A result at 5 sigma, the threshold physicists required before officially announcing the discovery of the Higgs boson in 2012, corresponds to odds of roughly 1 in 3.5 million of being a coincidence. The loophole-free Bell tests of 2015 cleared thresholds well beyond 5 sigma in most configurations, with some follow-up experiments in subsequent years pushing well past that, into confidence levels so extreme that the probability of local hidden variables somehow still being true, and simply getting lucky across every single test, becomes smaller than the odds of correctly guessing a specific grain of sand out of every beach on Earth, tried repeatedly, without a single wrong guess. It's like flipping a coin and calling heads correctly 70 times in a row, then being told the coin was fair the entire time. At some point, fair coin, remarkable luck stops being the reasonable explanation, and something about this coin, or this situation, actually is different becomes the only explanation left standing. But it gets worse for anyone hoping for an easy way out, because even after Aspect's results, defenders of local hidden variables didn't give up. They pointed, correctly, at the detection loophole and the locality loophole as genuine, unresolved technical gaps. And to their credit, this wasn't stubbornness for its own sake. In physics, you're required to close every loophole a critic can point to, no matter how implausible it might seem, before you're allowed to call a result final. Counterintuitive as it sounds, closing both of these loopholes simultaneously, in the same experiment, turned out to be a technical challenge that took physicists another 3 decades to fully solve. So what does this mean for the story so far? It means that for 30 years after Aspect's landmark experiment, the physics community operated under a strong, but not yet airtight, confidence that entanglement was real. Most physicists believed it. The statistical evidence was overwhelming. But a small, careful minority kept pointing out that until every loophole was closed simultaneously, in a single, unified experiment, Einstein's ghost couldn't be fully laid to rest. Here's where the story reaches its most decisive chapter. In 2015, within months of each other, 3 independent research groups announced they had run loophole-free Bell tests. A team led by Ronald Hansen at the Delft University of Technology in the Netherlands used electrons trapped in diamonds located in labs 1.3 kilometers apart on the university campus, entangling them via photons sent through optical fiber. A team at the National Institute of Standards and Technology in Colorado used entangled photons and ultra-fast, ultra-efficient detectors to close the detection loophole with room to spare. A team in Vienna, led by Anton Zeilinger, used an ingenious method involving light from distant stars to choose the measurement settings, making it essentially impossible for any local signal to have coordinated the outcome in advance. Let's walk through why the Delft experiment mattered so much, because it closed both loopholes at once in a single unified setup for the first time in history. 2 electrons, each trapped inside a diamond, sat in separate laboratory buildings across the Delft campus, physically separated by more than a kilometer of real distance. Each electron was entangled with a photon, and those photons were sent toward a third location roughly halfway between the 2 labs, where a specific kind of joint measurement caused the 2 distant electrons to become entangled with each other, a process physicists call entanglement swapping. The measurement settings on each side were chosen using a genuinely random process, generated fast enough and independently enough that no signal traveling at light speed could have carried information from one side to the other before the measurement was locked in. And because the electrons were trapped and measured with near-perfect efficiency, the detection loophole essentially disappeared too. The specific defect used to trap each electron is called a nitrogen vacancy center, a naturally occurring flaw in a diamond's crystal lattice, where a nitrogen atom sits next to a missing carbon atom, creating a tiny pocket capable of holding a single electron spin state stable for a surprisingly long time, even at room temperature, a property that made these diamonds unusually well suited for this kind of delicate, long-distance entanglement experiment. Ronald Hansen's team spent years refining the technique before running the final, decisive 2015 experiment. A reminder that a single landmark result in physics often sits on top of a decade or more of quieter, incremental engineering work that rarely makes it into headlines. The result, Bell's inequality was violated, again, decisively, with both major loopholes closed in the same experiment for the first time. It's called the loophole-free Bell test, and it's considered one of the most important experimental confirmations in the history of quantum physics. Here's what that means in real terms. Let's put it in context, because a kilometer might not sound impressive at first. It's like taking 2 coins on opposite sides of a mountain, flipping them at precisely, randomly chosen but independent instants, faster than any signal at the speed of light could cross that mountain to coordinate them, and finding that they land on the same face, correlated in a specific, quantum-predicted pattern, over and over again, far more often than chance or any hidden, pre-agreed script could explain. Not because someone rigged the coins in advance. Because the coins are, in some deep sense that no one fully understands, still connected, wherever they physically are. Not close to a loophole anymore, not a technical gap for skeptics to point at, closed. In 2022, the Nobel Prize in Physics was awarded jointly to Elaine Aspect, John Clauser, and Anton Zeilinger, explicitly for their experiments demonstrating violations of Bell inequalities and establishing quantum entanglement as an experimentally verified feature of nature, not a philosophical curiosity. It took nearly 60 years from Bell's original paper to that Nobel Prize. 60 years to go from a clever mathematical inequality to a settled, awarded textbook fact about how reality behaves. Let's walk through the Vienna experiment separately, because its method deserves its own moment. Anton Zeilinger's team faced the same core problem as everyone else. How do you guarantee that the choice of measurement setting on each side is truly random and truly independent, with no possibility that some shared cause reaching back in time, or some subtle signal, could have coordinated the two sides in advance? Their solution was almost poetic. They used light from real stars, thousands of light years away, arriving at each measurement station at the last possible instant to determine the measurement setting. The logic is elegant. If the measurement choice is determined by starlight that left its source centuries or millennia before either lab existed, then any conspiracy to fake the entanglement result would have had to be baked into the universe before human civilization began. Physicists call this a cosmic Bell test, and versions of it have since used light from quasars billions of light years away, pushing the conspiracy window back to nearly the birth of the universe itself. Here's what that means in context. It's like asking two witnesses on opposite sides of the planet to answer a question the instant they hear a specific radio broadcast originating from a transmitter so ancient and so far away that no one alive today, and no one who has ever lived, could have influenced what it would broadcast. If their answers still match up in the pattern quantum mechanics predicts, you've ruled out an extraordinarily wide category of possible cheating, going back an extraordinarily long time. So what's happening here across all three of these 2015 experiments, run independently, using entirely different physical systems, electrons trapped in diamond, photons detected with superconducting sensors, light gathered from distant stars. They all arrived at the same answer. Bell's inequality was violated. Local hidden variables, the version of reality Einstein hoped to restore, could not explain the results. What does it mean to live in a universe where this is simply true, where two particles, separated by any distance you care to imagine, behave as parts of a single system the instant either one is measured? It doesn't mean you can send messages faster than light. We'll get to why that safety valve exists later, and it's one of the most reassuring parts of this whole story. But it does mean that something Einstein considered too strange to be real turned out to be a permanent, tested feature of the universe you're living in right now, in this room, at this moment. Let's talk about what entanglement is actually used for, because by this point it had stopped being a philosophical curiosity and started becoming a tool. And the tool that captured the public imagination more than any other was quantum teleportation. But first, a brief detour into a technique that makes almost everything in this section possible: entanglement swapping. It's a natural question to ask. If entangled photon pairs are typically produced together, at the same source at the same moment, how do you ever manage to entangle two particles that have never been anywhere near each other? Particles created independently, in separate labs, possibly separated by enormous distances from the very start. The answer, developed theoretically in the early 1990s and demonstrated experimentally starting in 1998, is entanglement swapping. Take two separate entangled pairs, particles 1 and 2 from the first pair, particles 3 and 4 from the second. Perform a specific joint measurement, called a Bell state measurement, on particles 2 and 3, the inner particles from each pair. The remarkable result is that particles 1 and 4, which have never interacted, which may have been created in entirely separate locations and never brought anywhere near each other, become entangled with each other as a direct consequence of that measurement. It's the technique underlying the Delft loophole-free Bell test discussed earlier, and it's the same basic tool physicists use to extend entanglement across the intermediate relay stations, the quantum repeaters, needed to eventually stretch quantum networks across entire continents. Here's what that means in context. It's like taking two pairs of pen pals who have never written to each other directly, matching up one writer from each pair through a specific, carefully designed introduction, and discovering that doing so causes the two remaining writers, on opposite ends of the arrangement, who have never exchanged a single letter, to become correlated correspondents themselves, connected through a chain they never directly participated in building. What's happening here is not what science fiction trained you to expect. Nobody is disassembling a person atom by atom and reassembling them somewhere else. Quantum teleportation, first proposed theoretically in 1993 by a team of 6 physicists including Charles Bennett, and first demonstrated experimentally in 1997 by a team in Innsbruck, Austria, transfers the quantum state of a particle, its precise, complete set of quantum properties, from one location to another, using a shared entangled pair as the channel. The original particle at the sending location doesn't survive the process in its original state. Its exact quantum information ends up, intact, in a different particle far away. Nothing physical, no atom, no piece of matter, actually travels between the 2 points. Only the information, the pattern, does. Here's the analogy that actually captures it. Think of it less like teleporting a person and more like faxing a document. If the fax process destroyed the original page the instant the copy was printed, and the copy on the other end became, in every measurable way, the same document. That's closer to what's actually happening, though even that analogy strains at the edges, because what's being transferred is a full quantum state, something with no true classical analog at all. The most dramatic demonstration of this came from China in 2016 and 2017, with the launch of a satellite named Mencius, named after an ancient Chinese philosopher. Mencius carried a specialized crystal capable of generating pairs of entangled photons and beaming one photon down to each of 2 separate ground stations, sometimes over 1,000 kilometers apart, while maintaining their entanglement across that entire distance, through the atmosphere, through the vacuum of space. Let's put that number in context. The published result from 2017 demonstrated entanglement distribution over approximately 1,200 kilometers between 2 ground stations in China. That's roughly the distance from New York City to Miami. It's like standing in New York and flipping a coin, while a partner in Miami flips a second coin at exactly, independently chosen moments, and finding the 2 coins correlated in a pattern that no signal, not even one traveling at the speed of light between those 2 cities, could have coordinated in the available time. That's the kind of distance and precision that satellite achieved, using actual photons, actual detectors, actual peer-reviewed physics. The same collaboration also achieved ground-to-satellite quantum teleportation, transmitting quantum states from a ground station in Tibet up to the orbiting satellite across roughly 1,400 kilometers, a record that stood as the longest demonstrated quantum teleportation link at the time. Let's trace how we got there, because the road from Innsbruck in 1997 to a satellite over Tibet in 2017 wasn't a straight line. It was a slow, steady climb, one record at a time. The 1997 experiment successfully teleported the quantum state of a photon across a laboratory bench, a distance measured in meters, not kilometers, proving the theoretical proposal from 1993 actually worked in practice. Physicists then spent the following decade extending that distance, first through short stretches of optical fiber, then, in a striking outdoor experiment in 2004, across the Danube River in Vienna, sending entangled photons through a fiber optic cable laid inside a public sewer system beneath the riverbed, connecting a laboratory on one bank to a receiver on the other, a distance of about 600 meters, chosen specifically because it required the photons to survive a real, uncontrolled, outdoor environment rather than a pristine laboratory setup. By 2012, two separate teams, one in China and one working between the Canary Islands of La Palma and Tenerife, pushed the distance to roughly 100 and 143 kilometers respectively, using open-air, free-space transmission rather than fiber, specifically to test whether the atmosphere itself, and eventually the vacuum of space, could support entanglement over a distance approaching what a satellite link would require. Here's what that means in context. It's like watching a world record for a sprint slowly extend, year after year, from a few meters on an indoor track, to a few hundred meters through a city's underground infrastructure, to over 100 kilometers across open ocean air between two islands, each step deliberately testing a harsher, more realistic environment, building the confidence and the engineering needed before anyone was willing to attempt the same feat from low Earth orbit. Each of these experiments used at their core either the original 1993 teleportation protocol or a closely related idea proposed by the physicist Arthur Eckert in 1991, showing that entanglement itself, independent of Bell's original philosophical question, could be harnessed directly to guarantee secure cryptographic keys, a proposal that helped launch quantum key distribution as its own dedicated field of applied physics, running in parallel with the more foundational tests of entanglement's reality. So what does this mean for the future? It means that entanglement isn't confined to laboratory tabletops anymore. It's been stretched across the scale of a small continent, generated in space, and beamed down to the surface of a planet. Countries including China, the members of the European Union through the Quantum Internet Alliance, and the United States through Department of Energy testbeds, including a live network connecting national laboratories near Chicago established in 2020, are actively building what physicists call quantum networks, sometimes described as the early skeleton of a future quantum internet. Let's look at the scale some of these efforts have already reached. China operates what's often described as the world's longest integrated quantum communication backbone, a combination of roughly 2,000 kilometers of ground-based optical fiber connecting Beijing and Shanghai, first completed around 2017, linked together with the MISHIS satellite overhead to bridge distances too great for fiber alone to cover without prohibitive signal loss. The European Union's Quantum Internet Alliance, launched with European Commission funding starting in 2018, has set out a multi-phase roadmap explicitly aiming toward a continent-spanning quantum network by the early 2030s, treating the intervening years as a deliberate, engineering-driven scaling process rather than a distant hope. Here's what that means in context. It's like watching the earliest transatlantic telegraph cables get laid in the 1850s, expensive, fragile, prone to failure, covering only a fraction of the eventual need. Decades before anyone could have predicted the internet those first cables would eventually help make possible. No one laying cable across the ocean floor in 1858 was thinking about video calls. They were thinking about whether a signal could survive the crossing at all. Quantum networks today occupy roughly that same early, uncertain, foundational moment, measured in kilometers and error rates rather than finished infrastructure, but growing, year over year, with real government funding behind them. Here's the thing worth sitting with. This isn't a proposal on a whiteboard. It's kilometers of buried optical fiber, actual satellites in actual orbits, actual funding from actual governments, treating this once philosophical curiosity as critical infrastructure. Not because it lets you send messages faster than light. It doesn't. But because entangled connections allow for a fundamentally new kind of security and computation, one where any attempt to intercept the connection literally disturbs the quantum state and reveals itself. A built-in tamper alarm woven into the laws of physics themselves. Let's dig into why the speed limit holds, because it's one of the most important safety valves in this entire story, and it's worth understanding clearly rather than glossing over. This principle is called the no communication theorem, and it's been mathematically proven within standard quantum mechanics, not just assumed. When you measure your half of an entangled pair, you get a result, a specific outcome. But here's the crucial detail. That outcome on its own looks completely random. There's no way, just by looking at your own measurement, to know what your distant partner will see or to control what they'll see. The correlation between your results and theirs only becomes visible once you compare notes. Once the two of you bring your data together through an ordinary, classical channel, a phone call, an email, a radio signal, something that can never travel faster than light. Here's what that means in context. It's like two people each receiving a sealed page from the same shuffled deck of correlated cards at the same instant on opposite sides of the planet. Each person, looking only at their own page, sees a sequence of symbols that looks like pure noise, meaningless. Only when they physically bring the two pages together, later, using ordinary mail or a phone call, both limited by the speed of light, do they discover the pages were correlated the whole time, matching up in a pattern no classical shuffling could produce. The connection was real, the correlation was real, but the information about that correlation still had to travel the slow way. So what's happening in practice, in these quantum networks being built right now? What entanglement provides isn't a faster channel, it's a more secure one. In a protocol called quantum key distribution, first proposed in 1984 by Charles Bennett and Gilles Brassard under the name BB84, two parties use the quantum properties of entangled or individually prepared photons to generate a shared secret encryption key. If anyone tries to intercept the photons in transit, the very act of measurement disturbs their quantum state in a detectable way, alerting both parties that the channel has been compromised. It's tamper-evident communication built directly into the laws of physics, not layered on top through clever mathematics the way classical encryption works. But it gets worse for anyone hoping to build this quickly and cheaply. Photons get absorbed and scattered as they travel through optical fiber, losing roughly half their number for every 15 to 20 kilometers of standard fiber, which is why long-distance quantum networks need special relay stations called quantum repeaters, devices still very much in active development, to extend entanglement across continental distances without simply losing the signal to noise. Not simple, not solved everywhere yet, but real, funded, and advancing year over year, with the 2020 Chicago Area Quantum Network, connecting Argonne National Laboratory and Fermilab across roughly 40 kilometers of fiber, serving as one of the first dedicated testbeds for these ideas on American soil. Before we go further, let's pause on one more real-world application of entanglement, because it changes how you should think about everything that comes next. Entanglement isn't just the subject of exotic experiments in isolated laboratories. It's the working fuel of an entire emerging industry, quantum computing. Here's the thing that surprises most people. A classical computer, the one sitting in your pocket or on your desk, stores information in bits, each one a definite 0 or a definite 1. A quantum computer stores information in qubits, which can exist in superposition, a blend of 0 and 1 simultaneously, and critically, can be entangled with each other. It's the entanglement between qubits, not merely their individual superposition, that gives quantum computers their theoretical power. A system of entangled qubits can represent and process an enormous number of possible combinations simultaneously, growing exponentially with each additional qubit added to the system. Let's put a number on that. A classical computer working through a problem involving 50 entangled qubits worth of possible combinations would need to track over 1 quadrillion distinct states, a one followed by 15 zeros. In 2019, Google announced that its Sycamore processor, the same chip later used in the 2022 wormhole simulation, had completed a specific, highly specialized calculation in about 200 seconds that the company estimated would take the world's most powerful classical supercomputer at the time roughly 10,000 years to reproduce. IBM, a competitor building its own quantum hardware, pushed back hard on that estimate, arguing that with better classical algorithms, the same calculation could be done in a few days rather than 10,000 years, a disagreement that made headlines and highlighted just how young and contested this entire field still is. Let's put that disagreement in context. It's like two engineering teams arguing over whether a newly designed engine is 1,000 times more efficient than anything that came before it, or only 10 times more efficient. Both numbers would be remarkable. The argument itself is a sign of a genuinely new technology, still being measured, still being understood, rather than a mature, settled field. Here's the thing worth sitting with. None of this works without entanglement. It's the specific ingredient, not superposition alone, that allows quantum computers to perform certain calculations, particularly around cryptography, chemistry simulation, and optimization problems, in ways classical computers fundamentally cannot replicate through raw processing power, no matter how many transistors you add. Companies including IBM, Google, and a growing number of national research programs in China, the European Union, and the United States are investing billions of dollars into scaling these systems up, not because entanglement is a philosophical curiosity anymore, but because it's quietly become one of the most valuable known resources in the emerging technology of the 21st century. So what does this mean for the bigger story? It means that the same strange property Einstein tried to argue out of existence in 1935, the same spooky action at a distance he found so uncomfortable, has become, 90 years later, both a foundation of next-generation computing hardware and a candidate explanation for the very fabric of space itself. Not many ideas in the history of science have traveled that particular distance, from philosophical objection to industrial resource to candidate theory of everything. And entanglement has made that journey inside a single human lifetime and a half. There's one more practical thread worth pulling on here, because it connects the abstract mathematics directly back to something tangible. Quantum computers rely on a technique called quantum error correction to protect fragile entangled states from the outside noise that constantly threatens to destroy them. Tiny vibrations, stray electromagnetic fields, even cosmic rays passing through the hardware. Building a single stable, error-corrected logical qubit out of many noisy physical qubits, entangled together in carefully designed patterns, has been one of the central engineering challenges of the entire field since the 1990s. And steady, incremental progress on exactly this problem, spread across research groups at Google, IBM, and a growing number of university and government labs, has been part of what allowed experiments like the 2022 wormhole simulation to be attempted at all. None of it works without keeping entanglement alive, intact, and controllable for long enough to actually use it. A genuinely difficult engineering problem that connects the most abstract theoretical physics in this video directly to the most concrete, hands-on laboratory work happening today. So what's happening across the entire quantum computing industry right now, measured in raw numbers? IBM's roadmap, published in stages across the early 2020s, described a path from processors holding a few dozen qubits toward systems intended to hold well over 1,000 physical qubits, with error correction schemes designed to convert large numbers of noisy physical qubits into smaller numbers of stable, reliable logical qubits, capable of running genuinely useful calculations. Google, Amazon, Microsoft, and a rapidly growing field of dedicated quantum computing startups are pursuing parallel paths, using different physical systems entirely, superconducting circuits, trapped ions, and photonic qubits among them, each one representing a different engineering bet on how best to keep entanglement stable long enough to be useful. Let's put that race in context. It's like watching several competing teams in the earliest days of aviation, each betting on a different wing design, a different engine type, a different material, all racing toward the same basic goal of sustained, controlled flight, without yet knowing which specific approach would eventually win out, or whether more than one might succeed side by side. Quantum computing today occupies roughly that same early, competitive, unsettled moment, a little more than a century behind aviation on its own version of the same kind of timeline. Now let's turn to the part of this story that moves from confirmed experimental fact into the frontier of active theoretical research, the part where physicists start asking a much stranger question. If entanglement connects particles instantly regardless of distance, what if distance itself is the illusion, and entanglement is the underlying reality? In 2013, two of the most respected theoretical physicists working today, Juan Maldacena and Leonard Susskind, published a short, dense paper proposing something audacious. They called it ER equals EPR. The EPR stands for Einstein, Podolsky, and Rosen, the same 1935 paper we started with. The ER stands for Einstein and Nathan Rosen again, but from a different 1935 paper, one describing a theoretical structure called an Einstein-Rosen bridge, more commonly known today as a wormhole, a hypothetical tunnel connecting two distant points in spacetime through a shortcut. Here's the thing that makes this proposal so strange. Maldacena and Susskind noticed that the mathematics describing two entangled particles and the mathematics describing two ends of a microscopic wormhole share a deep structural resemblance, not a loose metaphor, a precise mathematical correspondence drawn from string theory and the study of black holes. Their conjecture states that whenever two particles, or even two black holes, are maximally entangled, there is a mathematically equivalent description of that same physical situation in which the two objects are connected by a wormhole, a literal tunnel through spacetime linking them. To understand why physicists were primed to take this seriously, you need one more piece of background: the black hole information paradox, a puzzle Stephen Hawking introduced in the mid-1970s that troubled theoretical physics for decades. Hawking's calculations suggested that black holes slowly radiate energy away, a process now called Hawking radiation, and eventually evaporate completely. But his calculations also suggested that this radiation carries no information about whatever fell into the black hole in the first place: a beloved book, a spacecraft, a star. If that's true, then when the black hole finally evaporates, all of that information simply vanishes from the universe forever, a direct violation of one of the most sacred principles in all of physics, the idea that information can never truly be destroyed, only scrambled or hidden. This became known as the black hole information paradox, and resolving it, or at least clarifying it, became one of the central projects of theoretical physics for the following 40 years. It's the same puzzle that motivated much of the SCFT research program, and it's the same puzzle that made physicists take entanglement's role in the structure of black holes so seriously by the time Maldacena and Susskind proposed ER equals EPR in 2013. Let's be careful about what this claim actually is and what it isn't. It's called the ER equals EPR conjecture, and it remains, as of today, a conjecture, not a confirmed law of physics. It has not been experimentally verified the way Bell's theorem has. It comes primarily from theoretical work in an area called the SCFT correspondence, a mathematical duality relating a theory of gravity in a curved space to a theory of particles on the boundary of that space, developed by Maldacena in 1997, and considered one of the most important theoretical results in physics over the past 3 decades. So what does this mean, practically? It suggests, at the level of mathematics rather than confirmed physical fact, that spacetime, the very geometry connecting one location to another, might not be a separate, fundamental ingredient of the universe. It might instead be built out of entanglement, the way a piece of fabric is built out of individual threads woven together. Pull the threads apart entirely, and the fabric doesn't just tear. It stops existing as a connected surface at all. Reduce the entanglement between two systems to zero, and according to this line of thinking, the spacetime connecting them in some deep sense disappears along with it. Let's put that in context with an analogy. Think of the internet as a physical structure made of servers and routers scattered across the globe. From the outside, it looks like distance matters. Los Angeles feels far from Tokyo. But the actual experience of using the internet, loading a page, sending a message, is defined entirely by the pattern of connections between servers, not by physical distance in the way a road trip would be. Two servers sitting right next to each other in different buildings can be, in a networking sense, farther apart than two servers on opposite sides of the planet if the connections between them are weaker. ER equals EPR suggests something similar might be true of spacetime itself. The geometric distance we experience, the feeling of one place being far from another, might be a readout of how strongly two regions are entangled, not a fundamental, independent stage on which physics happens. It's worth being precise about scale here too, because the wormholes described by ER equals EPR are not the kind you'd fly a spaceship through. The conjecture applies most cleanly to maximally entangled pairs of black holes, objects whose interiors, according to the mathematics, connect through what's called a non-traversable wormhole, one that pinches shut faster than any signal or object could cross from one side to the other, a far cry from the stable, walk-through tunnels of science fiction. Even the individual entangled particles produced in ordinary laboratory experiments, the same photons used in Bell tests and the MISHAS satellite link, technically fall under this same conjectured correspondence, connected, according to the theory, by some almost unimaginably small, almost instantly collapsing microscopic wormhole, far too brief and far too small to ever transmit anything through, but present in the mathematics all the same. Fascinating. Also, quietly, a little humbling, to think that every entangled photon pair physicists have ever measured might be threading an impossibly small, impossibly brief tunnel through the geometry of space, one so fleeting it leaves no trace beyond the correlation itself. What does it mean to look at the night sky and wonder if the space between you and a star isn't really there? In the way it feels. Not empty in the way we usually picture emptiness, but built, moment to moment, out of underlying quantum threads holding everything together at a scale far beneath anything we can directly perceive. In 2022, this theoretical idea took an unexpected, hands-on turn, and it's one of the strangest experiments to make headlines in recent physics history. A team of physicists, led by researchers including Daniel Jafferis at Harvard and collaborators at Caltech and Fermilab, used Google's Sycamore quantum processor, the same type of chip Google had used a few years earlier to claim so-called quantum supremacy, to run a carefully constructed quantum circuit. The result was published in the journal Nature in 2022 under the title describing traversable wormhole dynamics simulated on a quantum processor. Here's what actually happened, and it's important to be precise, because headlines at the time ran far ahead of the physics. The team did not open a hole in space. What they did was encode a simplified, highly compressed model, sometimes called the SYK model after the physicists Sachdev, Yi, and Kiddeev who developed it. A toy system that theoretical physicists believe captures some of the essential mathematical behavior of a quantum black hole, and ran it as a quantum information protocol on a 9-qubit portion of the processor. The protocol was designed so that information sent in on one side of the simulated system emerged out the other side in a way that matched the mathematical signature predicted for a traversable wormhole. A wormhole a signal could actually pass through, rather than the more common theoretical kind that collapses too quickly for anything to cross. Let's put that in context. It's like building an extremely simplified, tabletop scale model of a suspension bridge, not out of steel and cable, but out of a mathematical description of one, running a small ball through the model to confirm it behaves the way engineering equations predict a full-sized bridge would, and using that as evidence, not proof, but evidence, that the underlying equations are capturing something real about how actual cosmic-scale wormholes might behave, if they exist. The result made global headlines, some of them significantly overstating the claim, suggesting scientists had created a wormhole in a lab. The physics community's actual reaction was more careful and more interesting. Many physicists, including some involved in related research, pointed out that the experiment was fundamentally a quantum simulation, a specific kind of quantum computation designed to model wormhole-like information transfer, using a drastically simplified system with only 9 qubits, versus the astronomically complex system a real black hole would represent. Critics argued the experiment demonstrated a particular kind of quantum teleportation protocol, dressed in the mathematical language of wormholes, more than it demonstrated an actual, physical wormhole analog. The paper's authors themselves were careful in their published language, describing it as a proof of concept for studying quantum gravity using quantum processors, not a literal wormhole. But it gets worse for anyone hoping for a simple, clean answer, because both framings can be true at once. It genuinely was a simplified quantum simulation, limited by the tiny scale of current quantum hardware. And it genuinely was, according to the mathematics of the ER equals EPR conjecture, exploring the exact same underlying structure that would describe a real wormhole, if one could be built at a scale the universe actually uses. So what does this mean for where the science stands today? It means the ER equals EPR conjecture has moved from a purely theoretical paper into something researchers are now testing, in small, careful, heavily caveated steps, using quantum hardware sitting in real laboratories today. Not proof, not confirmation, but a genuine, active, funded, peer-reviewed research direction, treating the connection between entanglement and the geometry of spacetime as something worth building actual experiments around, not just writing equations about. Let's walk through the actual mechanics of the 2022 experiment a little further, because the details matter for understanding just how careful this claim really is. The SYK model, developed across contributions from Subir Sachdev, Jinwoo Yi, and later refined by Alexei Kidiev, describes a system of interacting particles whose behavior, under certain conditions, mirrors some of the quantum properties physicists expect near the surface of a black hole, particularly its tendency to scramble information extraordinarily fast, a property called maximal chaos. The Harvard Caltech Fermilab team constructed a deliberately simplified version of this model, sparse enough to fit onto a 9-qubit slice of Google's Sycamore processor, and used machine learning techniques to help identify which specific, simplified version of the model would best preserve the traversable wormhole behavior while remaining small enough to actually run. Here's what that means in context. It's a little like using a small, carefully tuned model train set, built to obey the same core physics of momentum and friction as a real freight train, to test whether a particular braking mechanism would work in principle, fully aware that scaling that mechanism up to an actual multi-ton train involves enormous engineering challenges the model can't capture. The model train result is genuinely informative. It is not the same as running the actual railway. Not close to a full black hole simulation. Not even close, in terms of scale. Real black holes are thought to involve something on the order of the astronomical number of quantum degrees of freedom implied by their entropy, values so large they dwarf the 9 qubits used in this experiment by more orders of magnitude than there are atoms in the observable universe. The media response was swift and, in places, wildly overstated. Several major outlets ran headlines describing scientists as having created a wormhole, framing it with the same imagery you'd expect from a science fiction trailer. And social media discussion in the days following amplified that framing far beyond what the underlying paper actually claimed. Several physicists not involved in the study, including some who worked directly on quantum gravity and holography, published rebuttals and clarifying commentary within days, arguing that describing the result as an actual wormhole risked badly misleading the public about both the current capabilities of quantum computers and the current state of quantum gravity research. This back and forth became, itself, a small case study in how difficult it can be to translate a genuinely interesting, genuinely careful piece of theoretical and experimental physics into a headline without something important getting lost along the way. So what's happening when a 9-qubit simulation generates this much genuine physics content and this much genuine public confusion at the same time? It's a reminder that toy model doesn't mean meaningless. Small, simplified systems have driven enormous progress throughout the history of physics, from Galileo rolling balls down inclined planes to approximate free fall, to Bohr's simplified model of the hydrogen atom in 1913, decades before quantum mechanics fully matured. Toy models are how physics usually makes its first tentative steps into genuinely new territory. The 9-qubit wormhole simulation belongs to that same long tradition, however unfamiliar its subject matter might feel compared to a rolling ball or a single hydrogen atom. But it gets worse, or better, depending on your perspective, for anyone trying to dismiss this as a media stunt. Because the paper went through the standard peer review process at Nature, one of the two most rigorous and selective scientific journals in the world, and the authors were transparent, in the technical language of the paper itself, about exactly what had and hadn't been demonstrated. The controversy that followed wasn't really about whether the experiment was real. It clearly was. It was about whether the popular framing, physicists create a wormhole, accurately represented what a 9-qubit simulation of a drastically simplified toy model actually shows about the universe. Many physicists in the field argued the accurate framing was closer to physicists demonstrate a specific quantum teleportation protocol, whose mathematical structure mirrors a simplified model believed to share features with black hole physics. A framing that, understandably, never made it into a single headline. Leonard Susskind, one of the two physicists behind the original ER=EPR conjecture, has continued pushing this research program forward in the years since, proposing, alongside collaborators, a related idea sometimes summarized as complexity equals volume, suggesting that the interior volume of a wormhole, or of a black hole itself, might correspond not to entanglement alone, but to the computational complexity of the quantum state describing it, roughly. How many steps it would take a quantum computer to prepare that exact state from scratch. Under this view, a black hole's interior keeps growing, long after it forms, not because more entanglement is being added, but because the quantum state describing it keeps becoming more computationally complex over time. A strange, information-theoretic explanation for something as physical sounding as the interior size of a black hole. It's a newer, more speculative extension of the same basic family of ideas, and it remains an active area of publication and debate as of the past several years, rather than a settled result. Is that not, in its own way, one of the strangest sentences you could say about a wormhole? That researchers built a version of one, however small, however simplified, however limited, on a chip, in a lab, using the same basic technology found in your phone's processor, just organized according to the strange rules of quantum mechanics. Let's revisit the deepest version of this question, the one physicists like Mark van Ramstonk, a theoretical physicist at the University of British Columbia, began asking seriously around 2010, A few years before Maldacena and Suskind's ER equals EPR paper formalized the idea mathematically. Van Ramsdonk published a paper, later recognized with an award from the Gravity Research Foundation, provocatively titled to suggest that spacetime itself is built up out of quantum entanglement. Here's the core argument, simplified. Using the mathematics of the AD-SCFT correspondence, Van Ramsdonk showed that if you take a system described by a quantum theory living on a boundary, and you gradually reduce the entanglement between two halves of that system down toward zero, the corresponding geometric description of spacetime doesn't just change, it tears apart. The connected, smooth geometry that would normally describe a single unified space splits into two disconnected regions, unable to communicate or influence each other in any way, exactly as if a wormhole connecting them had been severed. Reduce entanglement to nothing, and the space connecting two regions doesn't shrink. It stops existing as a connected space at all. What does that mean practically if it holds up? It suggests a picture of the universe that runs almost backward from how we usually think about it. We tend to imagine that space exists first, as a kind of container, and then particles get placed inside that space, some close together, some far apart, and their level of entanglement is a secondary property, something that depends on their history and interactions. This line of research suggests it might work the other way around. Entanglement might come first, in some deep, foundational sense, and the geometry of space, the very notion of close and far, might be a pattern that emerges from how strongly different parts of the underlying quantum system are connected to each other. Let's put this in context with the clearest analogy available. Picture a spider's web if you'll allow one final image. From far away, the web looks like a continuous, structured surface, with clear notions of near and far, center and edge. But zoom in, and the smooth-looking surface is entirely built out of individual threads, each connecting one point to another. There is no surface, independent of the threads. The surface is the pattern the threads make. Some physicists now suspect that space itself might work the same way. What looks from our vantage point like a smooth, continuous fabric stretching between the Earth and the Moon, between our galaxy and the next, might actually be woven, thread by thread, out of countless underlying entangled connections, at a scale so far beneath our everyday experience that we simply perceive the finished fabric and call it space. This remains, it's worth repeating clearly, one of the most exciting but genuinely unresolved frontiers in theoretical physics. It has not been confirmed the way Bell's theorem has. It has not produced a testable prediction in the way general relativity's bending of starlight was famously confirmed in 1919. What it has produced is a coherent, mathematically rigorous research program, actively pursued at major universities and research institutions around the world, treating spacetime from entanglement, not as a metaphor, but as a serious candidate for how the deepest layer of physical reality might actually be built. To understand why physicists take this conjecture seriously rather than dismissing it as wordplay, you have to understand where it came from, and that means talking briefly about black holes. In the 1970s, the physicist Jacob Bekenstein and, separately, Stephen Hawking discovered something strange about black holes. They behave as though they have entropy, a measure of hidden information, proportional not to their volume, the way you'd expect for an ordinary object, but to the surface area of their event horizon, the boundary beyond which nothing escapes. This became known as the Bekenstein-Hawking entropy formula, and it hinted at something physicists call the holographic principle, the idea that all the information contained within a three-dimensional region of space might be fully encoded on its two-dimensional boundary, the way a hologram encodes a three-dimensional image on a flat piece of film. Here's what that means in context. Imagine discovering that the total amount of information you could ever store inside a room depends only on the square footage of its walls, floor, and ceiling, not on how much empty air is inside it. Double the volume of the room without changing its surface area, and strangely, you haven't actually gained any new storage capacity. That's roughly the unsettling implication the holographic principle carries for the universe as a whole, and it was precisely this kind of thinking that led Maldacena in 1997 to propose the AD-SCFT correspondence, a mathematical duality connecting a theory of gravity operating in a curved, multi-dimensional space, called anti-de Sitter space, to an entirely different-looking theory of particles, without gravity at all, living on the flat boundary of that space. Two completely different-looking descriptions, mathematically proven to describe exactly the same physics. It's called a duality, and it's one of the most productive ideas in theoretical physics over the past 3 decades, cited in tens of thousands of subsequent papers. Calculations that are nearly impossible in the gravitational picture often become straightforward in the boundary picture, and vice versa, giving physicists a genuine mathematical Rosetta Stone for translating between two seemingly unrelated descriptions of reality. This is the toolbox Maldacena and Susskind were reaching into when they proposed ER equals EPR in 2013. Within this same AD-SCFT framework, physicists had already shown that the amount of quantum entanglement between two halves of the boundary theory corresponds precisely to the geometric size and connectivity of the corresponding wormhole in the gravitational picture. A result formalized mathematically in what's called the Ryuta-Yanagi formula, published in 2006, which calculates entanglement entropy directly from the geometry of a minimal surface inside the curved space. More entanglement, larger, more connected geometry. Less entanglement, smaller, weaker connection. Zero entanglement, no connecting geometry at all. Van Ramstonk illustrated this with a memorable example, imagining what happens if you start with a single, connected AD-SCFT system and gradually, mathematically, turn down the entanglement between its two halves, like slowly turning down a dial. At full entanglement, the corresponding geometric picture is a single, smoothly connected spacetime, with a wormhole running through its interior connecting the two sides. As the entanglement is reduced, the wormhole visibly stretches and thins in the mathematics, the geometric distance between the two sides growing longer and longer. And at the exact point where entanglement reaches zero, the geometry doesn't just become very long. It disconnects entirely, splitting into two separate, causally isolated spacetimes that can no longer influence each other at all, as if the space between them had simply ceased to exist. Here's what that means in context. It's like slowly loosening every single thread holding two pieces of fabric together, watching the fabric stretch and thin as you go, and then discovering that at the exact moment the last thread comes free, you're not left with two pieces of fabric connected by a very long, thin strip. You're left with two completely separate pieces of fabric, with no connection between them whatsoever, as though the strip itself had unraveled into nothing. The geometry didn't just get longer, it stopped being geometry at all. Not a metaphor invented for this documentary. A calculation performed within a mathematically rigorous framework, published in a peer-reviewed physics journal, and built upon by hundreds of subsequent papers over the past decade and a half, exploring exactly how much of the structure of spacetime, the notion of near and far, of curvature, of geometry itself, can be reconstructed purely from patterns of quantum entanglement in an underlying system that, on its own, has no built-in notion of space at all. So what does this mean for the biggest question of all, the one this entire video has been building toward? It means a growing, serious, mathematically productive body of research suggests that distance itself, the thing that makes a star feel unreachably far away, the thing that makes another person across the world feel disconnected from you, might not be a fixed backdrop the universe was built on top of. It might be closer to a readout, a kind of dashboard gauge, displaying the strength of underlying quantum connections that were there long before geometry ever organized itself into the shape we call space. What would it change, do you think, to genuinely believe that the emptiness between you and the farthest galaxy isn't really empty, and isn't really distance in the way it feels, but is instead a vast, intricate weave of connection, holding everything together at a level too small and too strange for any of us to directly sense? Before we arrive at the hopeful heart of this story, it's worth pausing on something that keeps this whole account honest. Physicists still disagree sharply about what any of this actually means, even while agreeing completely on what the experiments show. That distinction matters. The data is not in dispute. Bell's inequality is violated. Entanglement is real. Loophole-free tests confirmed it beyond reasonable doubt. What remains genuinely, actively debated is the deeper interpretation underneath those facts. And it's worth walking through the major camps honestly, rather than pretending physics has settled on a single, tidy picture. The Copenhagen interpretation, associated historically with Niels Bohr and Werner Heisenberg, essentially the view that won the original debate with Einstein, holds that a particle's properties genuinely don't exist in a definite form until measured, and that asking what's really happening underneath the measurement is, in some sense, not a well-posed question physics is equipped to answer. It treats measurement as a fundamental, almost primitive act, without asking too many questions about the mechanism underneath it. The many worlds interpretation, first proposed by Hugh Everett in 1957 and championed by physicists including Sean Carroll and David Deutsch today, takes a strikingly different approach. It suggests that superposition never actually collapses at all. Instead, every possible outcome of a quantum measurement really happens, branching the universe into separate, non-communicating copies, one for each possible outcome. Under this view, entanglement isn't spooky at all, because there's no instantaneous influence crossing space, just a single, deterministic, ever-branching wave function, quietly splitting into more and more parallel outcomes with every quantum event across the universe, including, this interpretation insists, every single quantum event happening inside your own brain and body right now. A third view, called pilot wave theory or Bohmian mechanics, developed by Louis de Broglie in the 1920s and revived by David Bohm in 1952, takes yet another route. It restores something closer to Einstein's original hope, hidden variables, particles that really do have definite positions at all times, guided by an underlying wave that can, explicitly and by design, exert influences across any distance instantaneously. Bohmian mechanics reproduces every experimental prediction of standard quantum mechanics exactly, including every Bell test result, but does so by embracing, rather than avoiding, a form of genuine non-local influence built directly into its equations. Here's what that means in context. It's like three separate, highly credentialed teams of detectives, all examining the exact same crime scene, all agreeing completely on every physical piece of evidence, the fingerprints, the timeline, the physical layout of the room, and yet arriving at three fundamentally different stories about what actually happened and why. Each story accounts for all the evidence. Each story is internally consistent. And for now, no experiment yet devised can tell the three detectives apart. So what's happening when a physicist tells you space itself might emerge from entanglement? It means they are, whether explicitly stated or not, generally working from a broadly Copenhagen-adjacent or information-theoretic starting point, treating entanglement as the primary, foundational ingredient. A committed many-worlds physicist might tell the same story slightly differently, framing the emergence of geometry in terms of the branching structure of the universal wave function instead. A committed Bohmian physicist might argue the geometric emergence picture is interesting mathematics, but insist that particles have real positions all along, making some of the space isn't fundamental language feel less urgent to them. Not a flaw in the science. A sign of a genuinely open, unfinished frontier, the kind physics has always had at its edges, going back to Newton's own unease about gravity reaching across empty space with no explanation. The experiments are settled. The deepest meaning underneath them is still being argued over by extremely capable people, in real time, in journals being published this year. Here's where this story needs to pause and breathe, because everything we've covered so far could sound unsettling if you let it. Reality not being what it seems. Distance possibly being an illusion. A universe stitched together out of connections instead of empty gaps. But there's a reason physicists describe this as one of the most hopeful frontiers in modern science, rather than a disturbing one. Whatever interpretation eventually wins out, if any single one ever fully does, notice something that stays true across every single one of them. Copenhagen, many worlds, Bohmian mechanics, all of it. In every single interpretation, the correlations are real. The connection between the two particles, however you choose to explain the deeper mechanism behind it, is not in dispute anywhere in physics. That's the part worth carrying forward into the final minutes of tonight's journey. Consider what it would actually mean if these ideas continue to hold up under decades of future testing. For the deepest sense of isolation any of us ever feel, looking up at a dark sky, feeling impossibly small and impossibly far from everything else out there. If space itself is built from entanglement, then in some strange, technical, but genuinely real sense, everything in the universe that has ever interacted, every particle that has ever touched another particle, carries a thread of connection to it, permanently, regardless of how far apart they later drift. The photons reaching your eyes right now from a star that burned that light thousands of years ago carry, in the language of this physics, an entangled history connecting you to that distant furnace of fusion, a thread woven into the fabric of the space between you. Not a comforting metaphor invented for a documentary, a mathematical structure, published, debated, and taken seriously by some of the most rigorous physicists working today. The universe may be, at its deepest level, less about distance and separation, and more about an almost unimaginably vast interconnected weave, one that simply presents itself to us, at our scale, as stars scattered across a dark and lonely-looking sky. Consider, too, what this means for the future of physics itself, rather than just the philosophy of it. If spacetime really does emerge from entanglement, then gravity, the force that shapes galaxies, bends light around black holes, and keeps your feet on the ground, might not need to be treated as a separate, fundamental force at all. It might turn out to be something closer to a byproduct, an emergent statistical effect arising from the underlying pattern of quantum connections, in the same way that the pressure of a gas emerges from the statistical behavior of countless individual molecules, without pressure needing to be written into the rules for any single molecule. This is roughly the direction pursued by physicists like Eric Verland, who proposed in 2010 that gravity itself might be an entropic force, not fundamental, but derived from deeper thermodynamic and informational principles. It remains a minority view, contested, unproven, and still being tested against astronomical data. But it sits comfortably within the same broad family of ideas this video has traced from 1935 onward. The growing suspicion among serious physicists that some of the things we've always assumed were bedrock, fixed, unquestionable features of reality, distance, separation, even gravity itself, might turn out to be beautiful, emergent patterns, built from something deeper and stranger underneath. So what's happening across 90 years of physics, from a thought experiment in 1935 to a quantum processor running in a lab in 2022? It's a slow, careful, rigorously tested unraveling of the assumption that separation is fundamental, not a single dramatic breakthrough. A long chain of smaller ones, each one a little stranger than the last, each one confirmed, checked, argued over, and confirmed again before physicists allowed themselves to believe it. One more thought before the recap, because it belongs here rather than earlier. Think about how strange it is that this entire body of research, From Einstein's 1935 paper through the Nobel Prize in 2022 and into the still unfolding work on emergent spacetime, has unfolded almost entirely out of public view, tucked inside physics journals, conference proceedings, and university lecture halls, while the rest of the world went on assuming that space is simply space, fixed, empty, and self-evident. That's not a criticism of anyone. Most of us have no reason to encounter this material in daily life, but it's worth sitting, just for a moment, with the quiet strangeness of it. Somewhere on this planet tonight, there are physicists who genuinely believe, based on real mathematics and real experiments, that the ordinary sense of distance most of us carry around every day might be one of the least fundamental things about the universe, and almost no one outside their field has any idea that belief exists. Tonight we explored 7 major discoveries spanning nearly a century of physics, each one chipping away at the idea that distance and separation are as fundamental as they feel. We began with Einstein, Podolsky, and Rosen's 1935 paper, which tried to prove that quantum mechanics was incomplete by pointing at what Einstein called spooky action at a distance, and their confident belief that hidden variables would eventually restore a more sensible, classical universe. We saw how John Bell, in 1964, transformed that philosophical disagreement into an actual testable inequality, giving physicists a real number to check nature against. We traced Elaine Aspect's landmark 1982 experiments, which violated Bell's inequality decisively, but left 2 critical loopholes open. We arrived at the loophole-free Bell tests of 2015, run independently in the Netherlands, Colorado, and Vienna, which closed those loopholes for good and led directly to the 2022 Nobel Prize in Physics. We watched Entanglement leave the laboratory entirely, riding aboard a Chinese satellite named Mischief, distributed across 1,200 kilometers of real distance, and used for quantum teleportation across even greater spans, laying the groundwork for quantum networks now under construction in China, Europe, and the United States. We stepped into the frontier of theoretical physics with the 2013 ER equals EPR conjecture, proposing that entangled particles and wormholes might be 2 mathematical descriptions of the same underlying object. And we saw that idea tested, in small, careful, heavily debated steps, on Google's quantum processor in 2022, and pushed even further by Mark van Ramsdonk's proposal that spacetime itself might be woven out of quantum entanglement, the way a fabric is woven out of thread. We also paused to be honest about what remains unsettled. 3 major interpretations of quantum mechanics, Copenhagen, many worlds, and Bohmian mechanics, agree completely on every experimental result while disagreeing entirely on what those results actually mean underneath the surface. A reminder that even a nearly 90-year-old Nobel-winning body of physics can still contain genuine, open philosophical questions at its foundation. And we saw Entanglement's quieter, more practical legacy too, powering the quantum computers now being built by governments and corporations around the world, turning what Einstein once dismissed as an absurdity into one of the most economically valuable resources in emerging technology. None of this means you'll ever teleport across a room, or that faster-than-light travel has quietly become possible while no one was looking. That's not what any of this promises, and it's not what any serious physicist studying it would claim. What it does mean is something quieter, and in its own way larger. It means the universe you're living in, right now, in this room tonight, might be built from connection at a level far beneath anything you can see or touch. A level where the vast, cold distances between stars and galaxies aren't the deepest truth about reality, but a kind of surface pattern, woven out of something far more intimate underneath. Think back for a moment to Newton, sitting with his letter to Bentley in 1693, troubled by the same basic discomfort that would trouble Einstein 2 centuries later. The idea that something could reach across empty space without anything obvious passing between. Newton never solved that discomfort himself. It took Einstein, building general relativity, to show that gravity's reach across space wasn't instant action at all, but curved geometry, rippling outward at the speed of light. And now, a century after that resolution, a new generation of physicists is asking whether Einstein's own resolution needs one more layer added beneath it, whether the geometry he described as curved and rippling might itself be built from something even more fundamental: entanglement, connection, thread upon invisible thread. It's a strange kind of relay race, handed down across 300 years, each generation of physicists inheriting the previous generation's unease about action across distance, and quietly, patiently, rigorously, working to explain it a little more deeply than the generation before. Human beings have always looked up at the night sky and felt small, felt distant, felt separated by gulfs of space too vast to comprehend. And yet the physics now suggests, carefully, provisionally, but genuinely, that the emptiness was never quite what it appeared to be. That every particle that has ever touched another carries an invisible thread forward through time. That the space between you and the farthest light in the sky might be less of a wall and more of a weave. Think about the sheer span of time this story has actually covered, from beginning to end. 91 years separate Einstein's 1935 paper from tonight. Long enough for a person born the year that paper was published to have lived through nearly the entire arc of this story themselves. Through Bell's theorem in 1964, through Aspect's experiments in 1982, through the loophole-free tests of 2015, through the Nobel Prize in 2022, and into whatever comes next. Physics, at its best, often moves at exactly this pace. Slow enough that a single human life can watch an idea travel from a handwritten thought experiment to an experimentally confirmed, technologically useful, and quietly world-reshaping fact about the universe. Not because physicists are slow to figure things out, but because getting it right, closing every loophole, satisfying every skeptic, building the instruments precise enough to actually ask the question, takes exactly as long as it takes, no faster, no matter how badly anyone wants the answer sooner. That patience is, in its own way, part of the hope this story carries. A civilization capable of spending 90 years, across multiple generations of scientists who would never live to see the final confirmation, chasing down a single, precise answer about whether two particles really can behave as one, is a civilization that takes truth seriously enough to wait for it. Consider the shape of this entire journey one more time, because it's worth sitting with the full arc before we close. It started with two men, Einstein and Bell, who never met, separated by nearly 30 years and a philosophical disagreement about what counts as real. It moved through a French laboratory in 1982, where photons generated from excited calcium atoms first hinted that Einstein might be wrong. It crossed into the 21st century, into 3 separate laboratories on 2 continents, closing every loophole a skeptic could imagine, and into a Nobel Prize awarded in 2022 for work that began nearly 60 years earlier. It climbed aboard a satellite named after an ancient philosopher, and beamed entangled light across 1,200 kilometers of open sky. And it descended, finally, into the strange mathematics of black holes and wormholes, into a 9-qubit chip running in a laboratory, simulating, in miniature, a structure some physicists believe might describe the deepest architecture of the universe itself. What ties all of it together isn't a single experiment, or a single theory, or a single physicist's insight. It's a pattern, repeating across 9 decades, in which distance, separation, and isolation, the things that feel most obviously true about the universe when you're standing outside on a cold night looking up, keep turning out to be less fundamental than they appear. Each time physicists have pushed hard enough on that assumption, tested it rigorously enough, built an experiment clever enough to actually ask the universe the question directly, the universe has answered with some version of the same surprising message. Things you thought were far apart might be more connected than they look. Human beings have always looked up at the night sky and felt small, felt distant, felt separated by gulfs of space too vast to comprehend. And yet the physics now suggests, carefully, provisionally, but genuinely, that the emptiness was never quite what it appeared to be. That every particle that has ever touched another carries an invisible thread forward through time. That the space between you and the farthest light in the sky might be less of a wall and more of a weave. Not empty, woven, not distant, connected, not separate, entangled all the way down. Sleep well and let the universe hold its threads a little closer tonight.